Hi, welcome back. This is still Ken and we're still on our course on mechanics, and this is lesson 4 on Newton's laws of motion. In the last video, we discussed about forces and interaction, and in this video, we're going to discuss finally your Newton's laws of motion. We begin with our study on the 3 laws of motion. We start with Newton's first law. Perhaps in your earlier high school years, you've known this law as simply stated as the following. An object at rest tends to stay at rest, and an object in motion tends to stay in uniform motion. But your Newton's first law is more properly stated as a body acted on by zero net force moves with constant velocity and zero acceleration. The essence of your Newton's first law is that objects don't start or stop moving on their own. There should be a net external force that will make the object move when it is at rest, or make the object stop when it is moving with constant velocity. Like say for example here, we have these apples on the table, and these apples are at rest or not in motion. And the only way that these apples will move is when an external force, such as say for example a person, or let's say an earthquake, will move these apples. Otherwise, if there is none, these apples will stay on their position forever and ever. Just a short question. Newton's first law of motion contains the phrase no net force. What does no net force means? The net force is the vector sum of all the individual forces acting on an object. If that is the case, your sum of all your F, or the sum of all your vector force, is equal to 0. Thus we say that your body is in equilibrium. And the X and Y component of your forces should also be 0, so that you get the magnitude of your vector F to be 0. And you can also extend this one to your Z-axis. Like for example, you have here a man sitting on a chair. The only way that your man is in equilibrium sitting on a chair is when the weight which is pulling down, the weight which is the pull of the gravity on the man, should be equal to the force that the chair applies on the man, pushing the man out. Otherwise, if they are not equal, then you can say, or we can imagine that, like say for example, if the weight is greater than the force of the chair, which is upward, if that is the case, the man will sink downward. But if they're equal, your weight and then the normal force, let's say the normal force that the surface of the chair exerts on the man are equal, then their forces cancels out. Thus the sum of all their forces is equal to 0. Our experience tells us that an object, such as a box being pushed across the floor, will stop moving if you stop pushing on it. This occurs because of the force of friction acting between the box and the floor. The friction resists the motion of the box. Now, what would happen if the force of friction could be eliminated? Let's say we make the floor frictionless. Okay, by Newton's first law, if there is no net external force, such as the force of friction acting on your system, and if you push the box and you let the box move at a constant velocity while pushing it, and the moment you stop pushing the box, since the floor is frictionless, there is no net external force, then what happens to the box is that it continues moving, or it continues to slide even if after you stop pushing it. And that is by your Newton's first law of motion. Your Newton's first law is sometimes referred to as the law of inertia. Loosely speaking, when we say inertia, inertia means laziness. Objects may be thought of as lazy because they don't change their motion unless forced to do so. Like say for example, you're sleeping on your bed, and this is one of the memes that is common to your Newton's first law. It says that the body at rest wants to stay at rest. And the only way that you'll wake up or you get out of bed is when You think about something that you need to do, or when someone pushes you to stay out of the bed. Like say for example, someone will throw hot water on you. So if that happens, there is already this net external force that makes you go out of your bed. The tendency of a body to keep moving once it is set in motion results from a property called your inertia. So you have your inertia to stay in your bed, to stay at rest. Okay. Let's test your understanding. In the classic 1950 science fiction film XM, a spaceship is moving in a vacuum of outer space, far from any planet, when its engine dies. As a result, the spaceship slows down and stops. What does Newton's first law say about this event? What do you think? Does this follow your Newton's first law, or does this violate your Newton's first law? Pause the video if you'd like to think more about this. The answer to this one will be posted at the end of this video. Another example, you're driving a Porsche Carrera GT on a straight testing track at a constant speed of 150 kilometers per hour. You pass a 1971 Volkswagen Beetle doing a constant 75 kilometers per hour. Again, you're driving a Porsche Carrera GT on a straight testing track at a constant speed of 150 kilometers per hour. You pass a 1971 Volkswagen Beetle doing a constant 75 kilometers per hour. The question is, for which car is the net force greater? Is it for the Porsche Carrera GT, or is it for the 1971 Volkswagen Beetle? For which car is the net force greater? Pause the video if you'd like to think about this question. And we'll answer this question on the last part of this video. Let's have some situation analysis. Suppose you're in a bus that is traveling on a straight road and speeding up, and you are inside a bus standing with roller skates, just like what is shown in the figure. Now, if you can stand in the aisle of, on roller skates, you would start moving backward relative to the bus as the bus gains speed. So you can observe that when the bus suddenly gains speed, you'd observe that you would move backwards like this one. If instead the bus was going to a stop, you would start moving forward down the aisle. So when the bus suddenly stops, you observe that you would move forward like that. In either case, it looks as though Newton's first law is not obeyed, so there is no net force acting on you, yet your velocity changes. What do you think is wrong? There's no net force that is pushing you backwards, nor no net force is pushing you forward, but why is it that your velocity changes? What's wrong with this situation? So to visualize this situation, we have here two scenarios. The first scenario, we have a bus that is accelerating forward. And then the second scenario, we have a bus that moves backward. On the first scenario, you are standing at the front end of near the front end of the bus. And let's say that the bus suddenly accelerates forward, and you would observe something like this. As the bus moves forward, you'd observe that you tend to move backwards, right? Or even if you're just standing on the bus without roller skates and you're holding at the bars, you observe that when the bus suddenly accelerates forward, you tend to move backward. And you can actually feel it, even when you are sitting. So even when you are sitting on the bus and then the bus suddenly accelerates forward, you observe that you are or you are something like pushed backwards towards your chair. For the second scenario, we have a bus that moves backward, or let's say that here the bus is this is also the same situation with the bus that suddenly stops. Okay, If the bus moves backward, you'd observe that you, standing in the middle of the bus with roller skates, tends to move forward. What do you think is wrong with this situation? So in the first situation, let's review. You're actually, or your inertia is that you are at rest. Okay, so your inertia on the first situation is you are at rest. And when the bus suddenly accelerates forward, your inertia will still tend to be at rest or will stay in that position. That is why what you see here is that it's something, or it looks like something that you are left behind on your initial position. So your inertia on the first scenario is that you're at rest and you tend to stay at rest. So what you feel that you are moving backward is that you're actually being left behind as the bus moves forward. Which is also the same scenario on the same case for the second scenario. So you tend to move forward when the bus stops, okay, like that. So you can observe that when you're sitting on a bus and then the bus driver suddenly hits the brake, you can observe that your body will move forward like that. The reason for that is because your inertia is, or your body is, or it tends to move. It tends to move with the bus. So you're moving with the bus. So when the bus driver hits the brake, your inertia will still tend to move forward. So that's why you feel this forward push as the bus suddenly stops. That is the reason why your seatbelts are very important, because as the bus moves, you're also moving with the bus. Your inertia is your inertia tends to be moving also. So when the bus stops, you will continue to move unless something stops you. Like say for example, unless you hit the glasses of the car or of the bus, or you hit the chair in front of you. So you will forever move forward when the bus suddenly stops, because you move forward unless something stops you, because your inertia tends to continuously move, and that is from your Newton's first law. But this is quite confusing, right? Now, in both the scenarios, okay, it makes you question, when is Newton's first law actually valid? So we have here another animation. Okay, so the bus is moving, and then the bus suddenly stops. But when the bus suddenly stops, you'd observe that you're actually continuously moving. Okay, this is what I was talking earlier. Unless something stops this roller skater, like say for example, if it hits the front end of the bus, okay, if there is none, then this roller skater will move forward until something stops him. In the animation, no net force acts on the rider, so the rider maintains a constant velocity, still moves forward even when the bus stops. But as seen in the non-inertial frame, which is your accelerating vehicle, it appears that the rider is being pushed. So it appears that you are being pushed forward when the bus suddenly stops. So your Newton's first law is valid only for inertial frames. When we say inertial frames, these are frames that are not accelerating. Otherwise, when your frame is accelerating, like say for example here, you have your frame, which is your bus, and then the bus is accelerating. Now this is what you call a non-inertial frame, and when you have a non-inertial frame, your Newton's first law is not anymore valid. Newton's first law again is valid only in non-accelerating inertial frames. The bus is accelerating with respect to the Earth, and in not a suitable frame of reference for your Newton's first law. A frame of reference in which your Newton's first law is valid is what we call your inertial frame of reference. We have already talked about your inertial or your frame of reference in lesson 2. The Earth is also accelerating. As you can observe, it rotates. So as it rotates, it changes its velocity, or it changes its direction of its velocity. So it's also accelerating. However, the Earth is at least approximately at an inertial frame of reference, but the boss is not. So we are accelerating with respect to the Earth, but we can approximate that the Earth is an inertial frame. As you can see, we do not feel the acceleration of the Earth. So at least approximately, the Earth can be considered a non-inertial or can be considered as an inertial frame of reference, but the boss is not, because the acceleration of the boss is very significant to the motion of your roller skater. So again, your Newton's first law is valid only in non-accelerating inertial frames. Now let's go to your Newton's second law. So your Newton's second law is stated that if the net force on an object is not zero, it causes the object to accelerate. So let's say, for example, here you have someone pulling you out of your bed. So there is a net force acting on you. So what happens is you tend to move out of your bed, you are accelerating. Another example is you push a car that is, let's say, at rest or is parked. So once you push the car, you're accelerating the car, you're giving the car some velocity. Also the same case with your lawn mower here. So as you push the lawn mower, your lawn mover accelerates forward. So if in your Newton's first law, there is no net force, in your Newton's second law, we now have a net external force that you're applying to your body. That this external force causes your body or your object to accelerate. The essence of your Newton's second law is that Newton's second law of motion tells how a force changes an object's motion. So how does an object's acceleration depend on the force, or what is the relationship with your acceleration and then the force that you're applying? So we have here in the figure an experiment which illustrates this relationship. And in the figure, it shows that when the acceleration is doubled, or shows that the acceleration is doubled when the force acting on a car on an air track is doubled. So you have here a spring balance to measure the force that you're applying on the what do you call that? You have here some mass on your air truck, and if you're going to apply just a small force on your mass, you observe that your mass will just move slowly. But you're going to apply a greater force, you'd observe that your mass will move faster. So in here, the acceleration of an object is directly proportional to the net force on the object. So the greater the force that you apply on your mass or on your body, the greater is its acceleration. Another example is when you're trying to pull something and then you pull it with a small force, you observe that it just moves slowly. But if you're trying to pull with a greater force, okay, you can move the body or the object at a faster speed. Next, how does an object's acceleration depend on the mass? Earlier we look for the relationship of your object's acceleration with the force. Now this time, we want to know how does an object's acceleration depend on the mass. So we have here a known force which causes an object with mass m1 to have an acceleration of a1, and we have another mass m2. We apply the same force, the same f, to the second object, and noting that the acceleration allow us to measure the mass. We can observe on the first figure, on figure A, that the mass is smaller. So your m1 is smaller to m2. And if you apply the same force, you'd observe that you accelerate mass m1 faster than how you accelerate mass m2, which has a greater mass compared to m1. And when you try to fasten the two objects together and apply the same force, you'd observe that the acceleration of the two bodies is slower compared to just having m1 alone or m2 alone. But in here, the smaller the mass the bigger the mass an object has, the harder it is to accelerate with the same force F. So the acceleration of an object is inversely proportional to the object's mass if the net force remains fixed. When we're actually talking about the mass is again the measure of the amount of matter, and your mass is a quantitative measure of your inertia. So the heavier the object is, or the more inertia that an object has, the harder it is for the object to be set into motion, or the harder it is for the object to be to stop its motion. Like say for example, you have a bicycle and then a truck. Which of the following two objects is easier to set in motion? If you're trying to push the bike and then the truck. Of course, here it is easier to push the bicycle than pushing the car or the truck, because the bicycle has a lesser inertia compared to the inertia of the truck. So here, the acceleration is inversely proportional to the object's mass. Okay? And if that is the case, the acceleration of an object, or we have stated earlier for the two relationships that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass of an object. If that is the case, then mathematically your Newton's second law is stated as the sum of all your F is equal to your mass times your acceleration, or this is the famous F equals ma. The SI unit for your force is again in newtons. So your Newton or your mass has a unit of kilogram, and then your acceleration has a unit of meter per second squared. So 1 Newton, which is the unit of your force, is equal to 1 kilogram times meter per second squared. If you're going to apply your Newton's second law, again, your Newton's second law is stated as the sum of all your F is equal to your mass times acceleration. Now, since your force and then your acceleration are vector quantities, the equation is a vector quantity, we will use it in its component form with separate equation for each component of force and the corresponding acceleration. So we have an equation for the x component, an equation for the y component, and an equation for the z component. Okay? If you observe for the first law, ma should be 0. Okay? So your first law is actually just a special case of your Newton's first law. Just take note that the sum of all your F means that it's the sum of all your external forces. And by the way, your Newton's first law equation is valid only if the mass is constant. And the equation is only valid in the inertial frame of reference. As we have stated earlier, your Newton's laws are valid only for inertial frame of reference. Just some caution. MA again is not a force. Some students may define, or when asked to define force, they say that the force is equal to the mass times acceleration. But again, your MA is not a force. The vector MA is just equal to the vector sum of all the forces acting on the body. But your MA is not the force. Let's have an example. A worker applies a constant horizontal force with magnitude 20 newtons to a box with mass 40 kilograms resting on a level floor with negligible friction. What is the acceleration of the box? So here we're given with the following quantities. Sorry. So again, here we're given with the following quantities. So we have a force, constant horizontal force with magnitude of 20 newtons. So we have 20 newtons. To a box with a mass of 40 kilograms, you have your M is equal to 40 kilograms. You're asked for the acceleration of the box. So our target is the acceleration A. Solving this one, you have F equals ma, and we want to solve the acceleration. So your acceleration is equal to F over m. So we have 20 newtons divided by 40 kilograms. So the acceleration of the box is equal to 0.5 meters per second squared. So that's how you're going to use your equation of your Newton's second law of motion. Some system of units, we will always use here your SI system. And by the way, in the British system, force is measured in pounds. Okay, so if you've heard pounds many times, especially in boxing, okay, so your boxers are measured in pounds. So the pounds is a measure of the force. Okay, the distance is in feet and the mass is in slugs. In the CGS system, your mass is in grams, your distance is in centimeters, and your force is in dynes. So in SI unit, your force is measured in newtons, your mass is measured in kilograms, and then your acceleration is measured in meters per second squared. So let's encircle these two interesting SI units. Okay, so for your mass, you have your kilograms, and for your force, you have your pounds, you have your lb. Okay, so here, this pounds here, or again, you've heard pounds several times when we're measuring the weight of your boxers. So they are actually measured in pounds. You'll never hear boxing tournaments measuring your measuring the weight of your boxers in terms of kilogram, because again, your weight is a force, so you cannot use your you cannot use kilogram in the kilogram unit in measuring your weight, because your weight is again a force. So if you want to measure your weight, you either use your Newton unit, or you can also use your pound unit. Okay, so next time when you are asked about your weight, like say for example in application forms or in biodatas or in information sheets, and you're asked of the weight, it's wrong to say that your weight is equal to 50 kilograms, because again, what is asked is your weight, not your mass. So if you're asked of your weight, you can use the newtons. So you have the acceleration due to gravity, which is 9.8. So you have your 50 kilograms times 9.8 meters per second squared. That is your weight in newtons. Or instead, you can use your pound measurement to put in your information sheet. Now, by the way, what's the difference between your mass and your weight? So here, your mass characterizes the inertial properties of a body. It's the amount of matter within your body. The greater the mass, the greater the force needed to cause a given acceleration. So if you have a greater mass, you're heavier, it is harder for you to accelerate. Weight, on the other hand, or the weight of an object, on the other hand, let's say the weight of an object on Earth, this is the gravitational force that the Earth exerts on it. The weight W of an object of mass m is given by your weight is equal to your mass times your gravity. This is just your F equals ma, but you have here your weight is equal to mg. So as you can see here, or if I'm going to ask you which quantity is constant? So which quantity is constant? Is it the mass or the weight? Let's say, for example, you go to Mars, okay, or we go to Jupiter, or we go to the moon. What is your mass on the moon? Let's say you have a mass of 50 kilograms. So what is your mass on the moon? So since the mass is just the amount of matter within your body, so your mass on Earth, your mass in Jupiter, your mass in the moon stays the same. It's still 50 kilograms, but your weight changes. So what is constant is your mass, your weight is not. Since different heavenly body has different acceleration due to gravity, so your weight changes when you are on the moon, your weight changes when you are on Jupiter or on Pluto, but your mass stays the same. So this is an easier picture of how you're going to differentiate your mass and then your weight. Mass is how much matter an object contains, while weight is the force exerted on mass by gravity. Mass is a constant for a body and does not change with location, while your weight is not constant. It changes from place to place. Again, technically, the pound is a unit of weight, but not of mass. So don't confuse now your mass and then your weight. Keep in mind that Newton is a unit of force, not mass. So we have incorrect expressions such as this box weighs 6 kilograms, which is actually grammatically correct, but in physics this is a wrong concept. So this is also nearly universal. What is meant here is that the mass of the box, probably determined indirectly by weighing, is 6 kilograms. So it's not the box weighs 6 kilograms. So in physics, you should have said this one as this box has a mass of 6 kilograms. Or probably that the mass of the box is determined indirectly by weighing is 6 kilograms. So it's grammatically right to say that the box weighs 6 kilograms, but you know that the weight should have a unit of Newton or in pounds. So you can correct it to say that this box has a mass of 6 kilograms. In SI units, weight is a force. This is measured in newtons, while mass is measured in kilograms. We're finally down to our last law of motion. This is your Newton's third law. It states that if you exert a force on a body, the body always exerts a force, which we call the reaction back upon you. This is the reason why your Newton's third law is also called your law of action and interaction, because for every force that you exert on the body will always exert a force on you with equal in magnitude but in opposite direction. Like say for example here, the figure shows an action-reaction pair. You have a soccer ball and then you kick your soccer ball with a force of Fa on B. Okay, so you are system A and then the ball is system B. So while you kick the ball, you apply a force of Fa on B, which goes to this direction. And since for every action there is always an equal but opposite reaction, so the ball is actually also kicking on you. So the ball applies a force Fb on A. So it applies a force F on you in the same magnitude but in opposite direction. But you are not actually being kicked backwards by the ball, right? But what you actually experience is if you're going to kick the ball more harder, you observe that your feet or your foot will hurt more. It's also the same case when you try to slap your friend on the face. Okay, you slap your friend in the face, but you're also experiencing a force that the face exerts on you, and that is by feeling some swelling on your hands. So it's not only that, or when you slap your friend harder, you also feel harder, or you will also feel more swelling on your hands, because that is the reaction that that the face exerts on you. So again, simply stating, your Newton's third law states that for every action, there is always an equal but opposite reaction. So that's it. You have your three laws of motion. So your first law is your law of inertia. Your second law is your law of acceleration. And then your third law is your law of action and interaction. We're going to apply these laws of motion in the next lesson.